about families of functions today. So a formula like f of x equals ax squared plus bx plus c describes a whole family of functions for different values of a, b, and c. So this particular family is called a three-parameter family because there are three constants a, b, and c that you can substitute different values in for. So we happen to know about this family. This is the family of quadratic functions, right, or parabolas. We can use calculus to help us understand the behavior of a whole family of functions, or to help us find a member of the family that has specified properties. So we know that this is the graph of a parabola, ax squared plus bx plus c. We want to find the parabola that passes through the point 1, 4, whose tangent lines at x equals -1 and x equals 5 have slopes 6 and -2, respectively. All right, so what is the fact that it passes through the point 1, 4? What does that tell us about the member of the family we're looking for? Yeah, if you set x to 1, the output of the function will be 4. So f of 1 will be a times 1 squared plus b times 1 plus c, which is just a plus b plus c, should equal 4. And then if you know that the tangent line, if you know the slope of the tangent line at a given point, what mathematical thing represents the slope of the tangent line? The derivative. So I know that the derivative when x equals -1 should be what? 6, yeah. So I'm going to take the derivative, plug in a -1, and that should equal 6. So f prime of x, this is just a polynomial, so I can just do the power rule. So f prime of x will be 2ax plus b. And I know that f prime of -1, because that tells me the slope of the tangent line at -1, would be, I plug a -1 in for x, I get -2a plus b. That should be 6. All right, and then I know f prime of 5. When I plug a 5 into my derivative, I should get -2, because the slope at -5, at 5 is -2. So if I plug a 5 in, I get 10a plus b equals -2. So now I have 3 equations and 3 unknowns, and I should be able to solve for a, b, and c. 3 equations, 3 unknowns. So I'm going to look at these 2 that just have the 2 variables in them, a and b. And I could either solve for one variable and substitute into the other equation, or I could subtract the 2 equations because they both have a 1b in them. So I'm going to go with that one. And I need some more space here. So I have -2a plus b is 6. And 10a plus b is -2. So I'm going to subtract the 2 equations. So -2a minus 10a is -12a. And b minus b is 0, so those cancel out. And then 6 minus -2 is 8. You can also think of it as just multiplying the whole equation by -1 and then adding the 2 equations together. Many people do that. So then I just divide both sides by -12. And so we get a is 3. What am I doing? Divide the top and bottom by 4, and I get 2/3, -2/3. All right, so I know what a is. I can use one of my two equations that had just an a and a b in it to solve for b. So I know that negative 2a plus b equals 6. You can just pick either equation, plug in negative 2/3 for a, and solve for b. So we get 4/3 plus b equals 6. So 6 minus 4/3, 4 and 4/3, which is 16/3. Did I do that right? Right. Well, 4 is how many thirds? 12/3, right? Plus another. Oh, 4 and 2/3, yes. Oh, what am I doing? Yeah, of course. That was 14/3. There we go. All right, and then to get c, I'll use the one equation that had a c in it, that a plus b plus c is 4. Yeah, a plus b plus c is 4. So negative 2/3 plus 14/3 plus c is, how many thirds is 4/3? 12, right? Just make this easier if I do everything in thirds. So negative 2/3 plus 14/3 is 12/3 plus c equals 12/3. So c has to be 0. Okay, so my parabola that I'm looking for, f of x, ax squared plus bx plus c, is going to be negative 2/3 x squared plus 14/3 x. That will have all the properties that they listed. Make sense? So GeoGebra is an ideal tool for analyzing families of functions. So let's use some sliders to demonstrate the problem that we just looked at. Okay, so let's consider another family of functions. You'll read about this in the book if you haven't already. Press record? Yeah, okay. F of x equals e to the negative x minus a squared over b. So this function is related to a useful tool in statistics called the normal density function. Often it's like referred to as a bell-shaped curve. So we're first going to analyze a simpler function, f of x equals e to the negative x squared over b. So in this case, a is just 0. So analyze it first with, then we're just going to take our results and shift them, because that minus a is an inside change to the function, and it's going to be a just shift left or right by a units. All right, so the analysis here is going to be tough. There's no hard and fast procedure that will work for analyzing every family of functions, but you do have the tools to reason through everything that follows. All right, so let's find the local extrema as well as the concavity. And we're going to start by figuring out end behavior. Okay, so let's look at the limit as x goes to infinity of e to the negative x squared over b. So as x goes to infinity, the top of that fraction is going to get really negative, right? So I'm going to be raising e to a bigger and bigger negative number. So where is that going to go? E to a big negative number. 0. Yeah. Yeah, if we just remember what e to the x looks like, right? And if we're raising e to something really large negative, right, e to that thing is going to go down towards 0. And then let's do the same thing for the limit as x approaches negative infinity. What do you think? It's the same thing, because even though it's negative, when I plug it in, it's going to get squared and give me the exact same thing as I did when I put in something positive. So my end behavior at both ends of this curve, at both extreme right and left, is going to head towards 0. All right, so we want to know where its local extrema are, as well as its concavity changes also. So extrema can happen where? Critical numbers. And critical numbers happen when the derivative equals 0 or when the derivative is undefined. So let's start by taking the derivative. All right, the derivative of e to some stuff is e to that stuff times the derivative of the stuff. What is the derivative of negative x squared over b? Yes, negative 2x over b. That b is a constant, right? Or you can think of it as a 1 over b. It's just going to come along for the ride. And then the derivative of negative x squared is negative 2x. So this ends up being negative 2x over b. Is that derivative ever undefined? When x, right. Yeah, there's no denominator here. There's no square roots, right? So there's no place where I have to exclude an x value. So I just want to know when this thing equals 0. Well, I'm multiplying two things together, right? I'm getting an answer of 0. So I could set each factor to 0 separately. So e to negative x squared over b equals 0, or negative 2x over b equals 0. E to something, does that ever equal 0? Nope. Again, look at the picture of e to the x. It has an asymptote at 0. It will never hit 0. E to the anything will never be 0. So this is never. And negative 2x over b equals 0 only if x equals 0. All right, so I have a critical number at 0. How do I determine if it's a max or a min? Yeah, I want to look at the sign of the derivative to the left and right of 0. Make myself a sign chart. Okay, so, and it's often easy to analyze a sign of a complicated function by breaking it into factors. Okay, so I'm going to look at the factor e to the negative x squared over b, and the factor negative 2x over b. Look at them separately, and then put them together to make f prime. Okay, e to the negative x squared over b. What is its sign to the left of 0? It's positive, yeah. What about to the right of 0? Positive, yeah. E to anything is positive. Even if the thing you're raising it to is negative, that just makes it close to 0, not negative, right? So e to the anything is positive, always positive. Negative 2x plus b, I'm sorry, negative 2x over b. To the left of 0, positive. Because it's already, we already have a negative sign. If you plug in a negative x, they're going to cancel and make a positive. Ooh, actually, assuming, what is that assuming? Yeah, that's assuming that b is positive. So maybe I should break this into 3 factors, negative 2x, and b. right? Depends on B too. So negative 2x is positive to the left of 0. And negative 2x is negative to the right of 0. And then B doesn't matter because it will have the same sign. Yep. Okay, so I can't put in negative to the left and positive to the right because this number line is representing values of x, right? So f prime is going to be different, right? It's going to be a max or a min in different situations. So B, we don't know exactly. Right? So assuming it's positive, so there's two different sign charts. Let's just assume B is positive to start. So we've got positives, positives, positives. Okay, so f prime then would be positive times a positive divided by a positive, which is positive. And then to the right of 0, positive times a negative divided by a positive is negative. So that means that f is increasing and then decreasing, which means that 0 is a max. Right? But if B is negative, these all become negatives. And my final signs will switch, right? And then f actually goes from decreasing to increasing, and we have a min. So it depends on the sign of B, whether it's a max or a min. So we have a local extreme. In either case, we have a local extreme at x equals 0. When B is positive, it's a max, and when B is negative, it's a min. Do they tell me anything about B? Nope. It does? Okay, good. Because that's what the normal density function looks like. It says a max. Okay, so we still have to analyze the concavity of this function. So if we assume b greater than 0, like the book, now we know that f of x has a max at x equals 0. Can we figure out its maximum value? What do I do to get the maximum value? Plug 0 into the original equation. Yeah, so f of 0. Remember, f of x is e to the negative x squared over b. So if I plug in a 0 for x, that's e to the 0, and I get 1. All right, so I know its end behavior. I know where its maximum is and what it is. And now I just want to know where its concavity, where its intervals of concavity are, where it's concave up, where it's concave down, where it changes concavity. All right, so what tells me about concavity? The second derivative. Okay, so f prime of x was e to the negative x squared over b times negative 2x over b. So if I want to take the second derivative, what do I have to do? Oh yeah, yep. So product rule, And it's not going to be as hard as it seems because I've already taken the derivative of e to the negative x squared over b. So it's not going to be too bad. All right, so we have first e to the negative x squared over b times the derivative of the second. What's the derivative of negative 2x over b? Negative 2 over b. Okay, so there's first times the derivative of the second plus the second times the derivative of the first, which I already know is negative 2x over b. No, sorry. That's not the derivative of the first. The derivative of the first is itself e to the negative x squared over b times negative 2x over b. All right, this seems like it could be simplified. Before I start trying to simplify, does it look like there's any place where that's undefined? Any values of x that I cannot plug in? No. Okay. So what I need to do is set this equal to 0, right? Because f is going to be concave up when f double prime is positive, concave down when f double prime is negative. Places where a function could change from concave up to concave down are places where the second derivative is 0 or undefined. Okay. So it's not never undefined, so I need to set this thing equal to 0. And I'm just going to hope that I can factor, right? So that I can do the set each factor equal to 0 trick. And I definitely have some things that I can factor out here, things that appear in both terms, like the e to the negative x squared over b. Is in both terms. And so is negative 2 over b. There's a negative 2 over b here, and then there's negative 2 over b appears twice in this factor, in this term. Okay, so this term, e to the negative x squared over b times negative 2 over b, if I factor both of those things out, all I'm left with is a 1. And then in my other term, this guy's gone. I factored that out. I factored out one of my negative 2 over b's. I know. Well, negative 2 over b is just a coefficient on x. I'm going to leave the x and take out the negative 2 over b. So I still have a negative 2 over b and an x and an x. So I have negative 2 over b x squared if I multiply those together. Right, so just to clarify that point you were just asking about, I was thinking of this as negative 2 over b times x. So I pulled out the negative 2 over b. All right, so that's still equal to 0. Now I can set each factor equal to 0. And I get negative 2 over b e to the negative x squared over b equals 0. Or 1 minus 2 over b x squared equals 0. This guy is never 0, right? We're assuming b is positive. And e to the something will never be 0, so this never happens. And then this guy says 2 over bx squared equals 1. So if I want to save this, solve this, get the x squared by itself, and I would have x squared equals b over 2. So x is plus or minus the square root of b over 2. So this is why we really have, now we have to assume b is positive, right? Because you can't take the square root of a negative. Okay, so let's take all the things we've discovered and try to draw a picture of this family of curves. Okay, so I know it has a max at x equals 0 with a value of 1. And I know the end behavior looks like this, approaches 0. And my changes in concavity are at positive and negative square root of b over 2. So it's going to go down towards 0, and it's going to start, concave up or concave down? It has to be concave down. There's no way I could draw it concave up, right? If I started drawing concave up, it would have to turn around to come to 0, which would mean I'd have another local max or min. So it's got to be concave down until radical b over 2, concave down, and then it switches concavity to concave up. Concave down, switches concavity. So right here, I did my best to draw it so that those are points of inflection. Yes.
I started skipping
The sign chart to determine whether it was a max or a min?
Like I would find my critical points and then do like just find
like f of 0, f of 0.1, and f of negative 0.1.
Something like a little bit past it on one side, past the other side, and say it's
That's this. You're doing the same thing. That's fine.
okay.
Yep. It's fine. Yeah, you're just making a mental sign chart. Good. Okay, so let's take a look at Geometry Sketchpad and see the real normal bell-shaped curve. All right, so here's the normal curve from statistics. It's a bell-shaped curve. It looks just like the curve that we just drew. It's got a maximum at x equals 0, a maximum of 1. Its end behavior approaches 0. And the change in concavity should happen at radical b over 2. And I have a slider here with b equal to 1. So that should be like 0.707. Should be my change in concavity, which is about right here. Looks about right. And then as I change b, it just changes the width of the bell curve. It changes where that point of inflection happens. It just gets wider and wider because the point of inflection happens at radical b over 2, which as b gets bigger, that point of that x value of the point of inflection moves to the right and to the left. All right, and then when I change a, this is just going to move my bell curve to the left and to the right. So it's just going to be centered somewhere other than 0. Okay, so your group work is the following problem, and then the exciting conclusion of the interpreting graphs series. So you've done 2 of those interpreting graphs problems. So I want you to find a function of the form at plus b over t that has a local min at the point 3, 12. Okay, so you're trying to find a member of this family that satisfies this condition. And when you're done with that, move on to interpreting graphs using calculus part 3.